Okay, so let's try to do depth first search on this graph. So we start with this vertex and we visit B. That's our, let me bold this. So it's our neighbor. So this will be our tree edge. So let me give it a green color. And so that's going to be the second vertex to be on this list, on the stack. And then from here we visit D using this edge as a tree edge. So this is going to be the third vertex pushed onto the stack. And from here we are going to visit this guy with a tree edge. So that's going to be fourth vertex on the stack. So now at F we don't really have any new vertex to visit because B is only one, but B is already on the stack. So this is going to be a back edge. So let me denote that like this. So that's our back edge. Okay. Now, so we are done with F. So that's going to be popped out from the stack. Then we backtrack to D. There's nothing else to visit from D, so we kind of pop out from D. And then there's nothing to visit from B2, so this is popped out. Now we are at A, so we will visit C, alphabetical order. So that's going to be the fifth vertex pushed onto the stack. So this becomes a tree edge because we're visiting the vertex for the first time. Okay, so then from C you will visit G using that edge as a tree edge. So that's going to be 6. And then from G you are going to visit this guy, so that's going to be this, and this is going to be 7. And we already visited A, so this edge is going to be our back edge. Alright, and we can then pop this out. So this is the fourth vertex, this is the fifth vertex to be popped out, this is the sixth vertex to be popped out, and this is the seventh vertex to be popped out. So this is our depth first search tree. Okay, now we want to find the articulation points. So as I said, you redraw this in the form of a tree so that it's more easy to visualize it. So you're having B and C as children. Okay, so this is B and C as children, and they are connected using a tree edge. So this is a tree edge. Then from B we have D, and then we also have F. So let me draw them, and then we can, so this is D and this is my F. So these are the three edges. and we have an edge from F to B, so that's the back edge. So let's draw that back edge from F to B. And now with respect to C and G, this is going to be our G, and this is going to be our E. Okay, so they are connected using a tree edge. Okay, so now we want to connect E and A through a back edge. Okay, so this is the depth first search tree. So now we want to decide which guys are the articulation points. So vertex A is an articulation point because it has two children, at least two children, in this case only two children. Okay, actually only two children, with connected through a tree edge. Okay, so that's the definition, that's the justification. Now, so I color them so this is my articulation point. Now E and F are not articulation points because why? They are leaf nodes. Now with respect to D, it is not an articulation point because there is subtree rooted at D, which is this subtree. Okay, now you see here from this subtree there is a back edge going above D, so which makes D not to be an articulation point. Okay, so D is not an articulation point because of the back edge from F to B. Similarly, let's look at B. For B, this is the kind of subtree, and there is a back edge, but it doesn't go above B, so which makes B to be an articulation point. Okay, now let's look at G. For G, we have this kind of subtree, and there is a back edge going from E to A, so G is not an articulation point. To the same argument, C is also not an articulation point because it's a back edge going from E to A. Right, so we can say vertices C and G are not articulation points because of the back edge from E to A. Okay, all right. You can also say B is an articulation point because the subtree rooted at child of B does not go beyond B, does not have a back edge go beyond B. So this is the kind of justification. Okay, now let's stop this.